Welcome back to this course on advanced memory hierarchy design. In this and the next lessons, I will describe compiler techniques to reduce the miss rate. In this lesson, I will focus on an instruction reordering technique, and in the next lesson, I will focus on data reordering techniques. This section is based on section 2.2, 10 Advanced Optimization of Cache Performance of the textbook by Hennessy and Patterson. In a paper from 1989, MacFarlane showed that he could reduce the cache misses of an 8 kilobyte direct map cache with 4 byte blocks by 75% in software. Although he performed these techniques manually by reordering the code or data layout, these techniques could also be performed by a compiler. In fact, many current compilers perform these techniques. MacFarlane applied instruction reordering as well as data reordering techniques. To reduce the number of instruction cache misses, he reordered the procedures or functions in memory to reduce the number of conflicts between them. He also used profiling to identify the conflict misses between basic blocks and reordered the basic blocks. To reduce data cache misses, MacFarlane also applied several data reordering techniques. I will discuss 4 of them in this lesson. Merging arrays is a simple technique that improves spatial locality and reduces conflicts by using a single array of structures instead of 2 arrays. Loop interchange is a technique that changes the order of loop nests to access data in the order in which they are stored in memory, thereby increasing spatial locality. Loop fusion is a technique that merges or fuses 2 independent loops that have the same looping to improve data locality. Finally, blocking is a technique where several nested loops are split so that the program accesses blocks of data repeatedly instead of accessing entire rows or columns that do not fit in cache. On the next slide, I will describe these techniques in more detail. First, let's look at procedure reordering. Suppose we have 2 functions, foo and bar, that are called repeatedly in a loop. Suppose also that foo and bar are placed in memory as illustrated in this figure. Foo occupies the blue memory segment and bar occupies the yellow segment. Now consider the placement of foo and bar in the instruction cache. First, foo is called and its code is placed at this position in the instruction cache, and then bar is called and its code is placed at this position. So each cache placement partially overlaps with foo and replaces a part of the code of foo. This code is reused on the next iteration when foo is called again. It would be better if bar would be placed at a position in cache that does not overlap with foo. How do we achieve that if we have no control over where the compiler places procedures in memory? Well, it requires some knowledge of the internals of the compiler, but usually a compiler allocates consecutive functions into consecutive memory segments. If the compiler allocates consecutive functions into consecutive memory segments, we can reduce the conflict misses by placing foo and bar consecutively in our program as sketched here. Then foo will be placed in the blue memory segment and bar will be allocated in the yellow segment that immediately comes after the blue segment. If now foo is called, it will be placed in this area of the instruction cache. And when bar is called, it will be placed here and here in the instruction cache. So it will be placed in an area that does not overlap the segment occupied by foo. Now foo and bar can stay in cache at the same time and no conflicts occur between them. This completes this lesson. Thank you for watching. In the next lesson, I will describe data reordering techniques to reduce the miss rate. Hope to see you back.